So apologies for folks online. I don't think, you missed some background, but I think the meat of it is just still on the horizon here. So, but yeah, just in terms of salinity, I mean, it's an interesting thing, right? There's all sorts of publications on it. I mean, you can read about how, salt accumulation in these ancient civilizations, ultimately led to their demise or contributed to it, right? So it's an important thing, and it's a problem today too, right? Not only in the Central Valley, but many other places in the country and in the world. So it's something that collectively we're all going to have to deal with. And, kind of salinity issues are sort of exacerbated by the way in which we manage water within our systems, right? And so by damming up, watersheds, and by, how we manage our irrigation practices, we can actually exacerbate our salt issues, right? Because you have salt coming into a system, and then if you have some of your water lost either through evaporation or transpiration, the salt stays behind. As the water goes up, you get concentrations, and over decades and centuries, it can really become a problem. So it's a long-term type issue in many cases. Just some specifics regarding sort of the current conditions in the Central Valley. On the left-hand side here, you can see a map of nitrate N concentrations in the upper aquifer. And so anywhere that is, colored red is above the drinking water standard, right? And so as you can see, there's certainly areas in the valley that are, substantially impacted by nitrate at this point in time. Additionally, on the salt side, some sort of mass balance calculations that DWR has done is kind of just demonstrating that in terms of sort of, transbasinal salt movement or import of salt into our watersheds. We have a lot of salt coming in through the Delta, right? And those water imports that get transported south to the southern portions of the Central Valley. We also have salt coming in with from sort of the mountains of our watershed. So on the Coast Range and on the Sierra Nevada side, there's, relatively dilute amounts of salt, but over time, year after year, it does add up, right? And so, we constantly have salt entering our system. And then, as I kind of described before, when you have evaporation or transpiration processes concentrating that salt, moving it back below the root zone in the case of agriculture, it's accumulating, right? And so that's kind of where we're at, and sort of the impetus for, addressing these issues with a tool like SWAT. And so that's a good segue. Why use models, right, at all? And I think, again, folks probably have some snappy answers to this, but I'll just say them anyways. In the case of, especially in the case of non-point source pollution, like discharge from a root zone, it's a really hard thing to measure, right? And it's a hard thing to measure at scale. And so when we're talking about the Central Valley, we're talking about millions and millions and millions of acres. There's a lot going on there, and the valley itself is extremely complicated, not only in terms of hydrology and hydrogeology, but how water is managed, all the different crops are grown, the different irrigation infrastructure. There's a ton of variability, right? And so to try to monitor and measure what's going on across the whole system is, daunting, to say the least, right? And so, that's kind of where models come in, right? Like, models can help us, not only try to understand current conditions today, in terms of magnitude of, say, nitrate loading or salt flux, but they can also kind of help us understand what sort of management strategies may or may not be helpful to mitigate these issues, right? And so that's really a super helpful piece of the puzzle there. And you'll see how we kind of use SWAT to look at, what can we do, or what do we need to do to resolve some of these water quality issues moving forward. And so that's just kind of models in general. And so why SWAT/SWAT plus? There's a long list of reasons. And I think you guys have probably learned a bit about some of its strengths at this point. But, again, since we're talking about sort of a regional scale issue here, and it's a big region in the Central Valley, you kind of want a tool that's able to kind of reflect, to be able to function at such a big scale, and also kind of maintain some of the spatial granularity and nuance that we know is occurring within the system. And so SWAT is very much designed to do that, very feasible to implement at the scale. We've done it, so we know it can be done. It's physically based and comprehensive. And given that the Central Valley is really an agricultural dominated system, we want to be able to represent agriculture well, right? What's going on in the root zone, what's going on with crops, how are these crops managed in terms of fertilizer and irrigation. We want to be able, what are the impacts of local soil and climate on nutrient management. We want to be able to reflect all of that in a tool, and SWAT kind of gives us that ability. And so, sort of early on in the process of figuring out tool selection or approach, to deal with nitrate issues, SWAT kind of rose to the top of the list in terms of checking all the boxes that we needed checked in order to address these issues. There's other tools, there's other approaches that are certainly viable or certainly, have their merit as well. But SWAT really kind of, again, checked all the boxes in a pretty good way. So focusing now, kind of diving a little more into nitrate, we kind of have it broken up. We'll talk nitrate and then we'll talk salt. So for a little bit more background, I'm not sure if folks are aware of the Irrigated Lands Regulatory Program, but that is a regulatory program that regulates dischargers on their discharge of nitrate. And initially, the orders were passed to regulate surface waters, but then in 2012, the orders were updated to protect groundwater, realizing that not all water discharge goes to a surface pathway. A lot of it goes below the root zone and eventually into the aquifer. And so the goal of this regulatory program is to try to restore and or maintain the highest reasonable water quality while maintaining economically viable agriculture in the Central Valley. And so in response to this regulatory order, growers organized and formed what are called water quality coalitions, 14 of them to be exact, which you can see in this map here on the right-hand side, spanning the Central Valley. And so it's comprised of over, 24,000 irrigators. We're talking about, 5.5, 6 million acres, something like that. Big area, a lot of growers. But that's sort of the entities that have organized to respond to the orders and do, collectively what they need to do to be in compliance and to protect groundwater quality from nitrate. So basically those water quality coalitions, after some time in deliberation, they needed to choose a way in which to assess themselves under this program, right? And so did they want to use, spreadsheets? Did they want to have monitoring wells in every field? Did they want to, use a robust physically based, model? I'm setting up SWAT here. And so ultimately that's what they chose, right? Was to adapt CV SWAT because they realized, all the merits that I've already described, this tool would be able to reflect, details about the nitrogen cycle, details about management, details about hydrology, integrated soil, climate. It's super comprehensive. And so it was kind of a no-brainer at the end of the day. And so without getting into too many details, there are various facets and components of the ILRP. There's two components that SWAT really kind of directly plugs into. It's kind of involved in some others in some ways, but really that I think the focus would be on sort of the management practices evaluation program, as well as the groundwater protection program. And I think those names are pretty self-explanatory in terms of what they're all about. And a tool like SWAT will help you understand, what are the impacts of management on outcomes like nitrate leaching, and, help us estimate, how much nitrate do we think is currently discharging relative to how much do we think we need to discharge to be protective of water quality. So the adaptation or the development of CV SWAT was initially carried out by one of the MPEPs. There's two MPEPs. And this work was done in collaboration with NRCS and UC. The SSJV MPEP was awarded a conservation innovation grant from the NRCS for $2 million, and a portion of that helped fund the development of CV SWAT, as did significant contribution from the ag community as well. And so the whole idea here was, okay, let's spin up a SWAT model that's reflective of what's going on here. Let's get the appropriate climate and soil. Let's calibrate our crop models such that they're reflective of these highly productive systems, transpiring at appropriate rates, taking up and removing appropriate amounts of nitrogen. Let's get that spun up. and do that for basically the vast majority of the valley, so that we have a really good model that can kind of tell us what's going on across the landscape. And so I'll get a little bit into the weeds about some of the setup. Usually I gloss over this stuff, but since we're at like a SWAT training session, I can go into a little more detail anyways. You guys have an appetite for it. But so, first and foremost, I'm sure you've been educated on this matter. Like, your inputs into your models are critical, right? The better your inputs are, whether that be, environmental factors, whether that be how you calibrate your crop models, all those inputs are fundamental to getting a good answer on the back end, right? And so we took a lot of care and time kind of in each piece that I'm going to talk about to set up our model, so that by the time we're actually estimating nitrate leaching, we have as much confidence in it as we can, right? And so on the climate side, California has the CIMMYS network, which was great and very useful for us in this application. And so basically we compiled the CIMMYS record from right now, it's going back to 1983 up till somewhere around present, plus or minus a couple years, but fairly long record, 38, 40-year record, something around there. And the key variables that we're taking from CIMMYS to actually run our SWAT model are solar radiation, right? That's going to drive, production of biomass, right? With our crop models, relative humidity and wind speed, that's going to affect our ET. Temperature is going to affect a lot of things like crop growth, nutrient cycling, things like that. And of course, precipitation is really important to the water balance. But so all these variables are coming directly from CIMMYS. We have daily information for each of these, and we're plugging them directly into our model. On the soil side, and I am a soil scientist by training, so this is a passion slide as much as anything. But there's many different options for soil input data that you could plug into SWAT. And so there's StatsGo data set, which you may be aware of, which is fairly coarse in terms of resolution. There's the Surgo or GSurgo, which is finer than StatsGo, another NRCS product. And then on top of that, there's I'm just calling it the NCSS database, which is essentially a collection of data and information that's really derived at sort of the PEDON scale or the soil pit scale. So, pedologists, soil surveyors go out, they dig a hole, they horizonate, they take samples from each horizon, bring it back to a lab, have it analyzed for things like texture, bulk density, carbon, all these various properties. And, obviously there's a lot of detail in there, right? But these are sort of the options, and there are other options too, depending on where you are in the world. But kind of serendipitously, the NRCS, under their conservation effects assessment program, those modelers over in that program were actually developing their own Central Valley SWAT model kind of at the same time we were starting to. And so we saw it as a great opportunity to sort of collaborate and not create redundant work. And so actually some of their developers were basically took the NCSS data set and sort of merged that in with Surgo, right? And so where we had, this PEDON, this highly detailed PEDON data to describe various mapping units, as opposed to Surgo, that information was plugged in. Another important step that we did was basically recalculating hydraulic conductivity, which is a really important physical parameter that's going to govern how quickly water, nitrate, and salt move through a soil profile. We did that with pedotransfer functions published by Saxon and Rawls, widely used. And that not only kind of standardized, but there's some data gaps, right, in terms of some of these harder to measure properties. And so, using pedotransfer functions, which are just, models, right? So if your sand, silt, clay, bulk density, carbon content, then you can compute a reasonable hydraulic conductivity based on those more readily measured properties. And then of course, like any good modeler, we checked all of our properties for consistency, range, and interrelationship. And at the end of the day, at the whole watershed scale, there's over 9,000 unique mapping units for soil specifically. And this is comparing SWAT Surgo to our PEDON data set. This is an old version of SWAT Surgo, so it may look different now. This is from a couple years ago. But this just the point we're trying to make is that the PEDON basically we see sort of a wider distribution in terms of soil depth for any given mapping unit, as well as, more mapping units with additional vertical detail in terms of the layering and how the properties associated with each of those layers. And so the Sergo tends to be more of an aggregated product. And so we were able to sort of disaggregate that a little bit and get a little bit more field-based data into our soil data set. There's just a visual showing the difference between StatsGo and Sergo for the Central Valley watershed. Clearly substantial differences in terms of detail. And after our pedo transfer functions, you can see that there's kind of a little bit more consistency and connectivity across soil parameters. And so what I'm showing here is the hydraulic conductivity for the first layer of various mapping units, and on the x-axis here, we're grouping these distributions by soil hydrologic group, which is really just sort of an index for runoff versus infiltration. And so soils that fall into A tend to be more permeable, infiltrate more water. Therefore, they're usually a function of coarser textured soils, right? And as you move towards D, it's the opposite. There's more runoff. And so we can see that the hydraulic conductivity better follows that trend after we've implemented these pedo transfer functions. So just a little soil science background there for you. And in terms of management, this is really important and sort of the crux of the management practices evaluation program, right? And the California, because how you manage corn silage here is going to be very different than it is in Iowa, right? And so we want to be sure that we're using practices that are reflective of here. And so we spent a lot of work, invested a lot of time, used a lot of industry contacts and resources, basically leveraging the extensive UC extension system, talking with local advisors about how crops in their domain are managed, basically to inform. Here in the Central Valley, growers are also required under the ILRP to submit what are called irrigation and nitrogen management plans or summary reports. So these are INP reports. You might hear this term moving forward, but that basically tells us, what crop a grower grew, on how many acres. We know where it is because of parcel information, the applied fertilizer rate, and we know the total yield. And so we can compute from that a partial mass balance or a partial N balance. So if we know applied, we know removed, what happens to what's left over, right? Not all of it leaches, right? We know the nitrogen cycle is more complicated than that, but what does happen to that? SWAT helps us kind of figure that out, right? Or get a better estimate for it. So we're able to use that information to inform management in terms of fertilizer rates, yields, and the relationship between the two. And when we actually set up, for various crops and various watersheds, we're actually detailing out management schedules, like building, we irrigate this much water on this day to reach salts in the winter. We fertilize at this point in time because that's the best management practice recommendation when crop demand is highest for nitrogen. That's, so we kind of fold in UC's advice in terms of how you would manage these crops. On the irrigation side, we basically operate under the assumption that, or we take the sort of the dominant irrigation infrastructure. We know there's generally a conversion to micro sprinkler and subsurface drip. Some crops are still grown, furrow irrigated or flood irrigated. So if that's sort of the common practice for a given area, that's how we model it. I also added in fertilizer types, kind of has some implications for your ammonia volatilization calculations, right? So if you're not applying ammoniacal-based fertilizers, SWAT's not going to simulate any ammonia volatilization, right? So fertilizer type is important. And we've basically also tailored that to sort of what's representative of what's going on in the valley. And again, this is all to the point of, the better you can inform your model, put inputs into your model, the more confidence you have in the answer coming out on the other side. And so this was done for about 40 to 50 crops for each watershed. We got the 3 watersheds. So, quite a bit of work done there to sort of locally, if you will, reflect, how these crops are grown. Now for the crop model calibration, this is, paramount to everything, in terms of our modeling. And this was sort of done, manually, right? So this was an iterative process, right? And so, SWAT will give you sort of default values for the various parameters. But, in working with sort of, UC folks, industry experts, we kind of have an idea of, what our target biomass is for a given region. We have all sorts of estimates for ET, whether it be satellite based or Siemens based. We kind of know, have a good idea about what to expect or to shoot for in terms of transpiration. On the nutrient uptake side, there's a lot of good work done for a lot of the major acreage crops in terms of, what that uptake curve looks like throughout a growing season, how much total nitrogen is taken up. We have a good idea about, what kind of yields growers are getting because they're telling us, right? We also have, other, more publicly available reports like Ag Commissioner reports. And so, how much biomass, how much yield, how much nitrogen is being removed with that yield. All these things are really important for a nitrogen and water balance, right? And so they kind of guide our calibration process. And because we don't necessarily have like a stream gauge that we want to auto calibrate our flow to, we're talking about, hundreds of thousands of fields all managed differently. All the annual fields are rotating across. We don't have kind of the data set that, some might expect you would need to do sort of an auto calibration type procedure. And so this was very much manual. This was very much interpretation of results, reviewing, checking against the information we do have to make sure that we're building something that is reasonable and defensible and consistent with the data that we do have. So, I mean, this is years of effort really to get these crop models where we wanted them to be. For you modelers, this is pretty dense, but just in terms of, what crop model parameters are important or that we found to be important that we paid particular attention to when we were calibrating. The list is fairly long, but basically it boils down into parameters that are governing how much biomass is being produced, canopy development, which is going to influence how solar radiation is intercepted. It's going to influence your evapotranspiration dynamics. Your growing degree days or heat units, how quickly are those accumulated? How does your plant mature? How quickly and when? Obviously, canopy height and root depth are important. How much nitrogen is removed with your yield. These BN 1, 2, and 3 parameters basically in SWAT, you're basically setting what is an optimal nitrogen concentration in your biomass at emergence at 50% maturity and at maturity. And that's going to drive nutrient uptake in your model, right? And so setting these parameters is, really important for modeling leaching at the end of the day, right? Because if you were either undershooting or overshooting, your leaching numbers would be directly affected by that. And so having good nitrogen uptake curves is really important. We did actually find that some other parameters sort of regarding somato conductance and how that impacts radiation use efficiency. Those are pretty, there's not a whole lot of data on them, but they're pretty sensitive levers. So just be aware that those are important. And what we have on the right-hand side is just an example of some default parameters in the crop database, SWAT database that we further calibrated for Central Valley. And, in the case of processing tomato, it's, there are some differences for sure. Harvest index, substantially different. Potential leaf area index, definitely different. But I was actually quite amazed that the CN yield or how much N is removed with your harvest was actually remarkably similar. And we've gone through a lot of work with a separate project working with the processing tomato industry to collect, if not, I think hundreds of samples of processing tomato being removed from fields all over California. And this is the number we came up with after collecting data for 3 years. And SWAT guys were actually pretty close. And so I don't know if that's luck or what it is, but it was just surprising to me when we were putting this table together. I was like, wow, that's something. But yeah, and then some other things right on the basin parameters, because we're so focused on the nitrogen cycle here, we want to be cognizant of how much denitrification is occurring, calibrating to that. Are we accumulating soil organic matter in our soils? Or are we depleting our soils? Are the residues from our crops breaking down all the way? All these different pieces matter, right? Because at the end of the day, it's going to drive what your leaching number is. And so, we found that, we had to actually increase the CMN, which is basically a mineralization rate factor, to ensure that, the residues left behind after harvest were fully breaking down over the course of our simulation. Otherwise, you can essentially have a net accumulation of nitrogen. And, in an organic system with a lot of cover cropping and residue inputs, like maybe that's the case, but in a conventionally managed, heavily tilled system, probably not, right? And so we have to be careful about all that. And so these are all the sorts of things that we paid a lot of attention to in the model calibration process. So at the end of the day, we were able to model about just under 99% of the grower reported acreage, right? So they tell us what they're growing. And so we got dang near all of it. And you can see there's sort of diminishing returns in terms of another 5, 10, 15 crops might only get us, 0.1% of the acres at this point. And there may not be that much data to really even drive our calibration process. And so we got the big ones. So that's a big accomplishment there. And then, so with respect to the groundwater protection program, again, this is under the ILRP. I'm not going to go into a lot of details about this, but basically SWAT was used to estimate, basically in conjunction with grower data. We use that's the formula is basically data and methods where we use grower data in the SWAT model, and I'll show you how we did that to compute what are called groundwater protection values, which are essentially township-based leaching estimates. So townships are 6 mile by 6 mile grids that we have out here in the West for zoning. And so essentially, the formula and the values in SWAT is really used to characterize what's going on within the root zone of irrigated agriculture. And then, we had to set targets, which are basically looking at the whole system, what's happening with recharge, vadosome, groundwater processes, to basically try to determine how much leaching is okay, such that irrigated ag is not causing or contributing to, an exceedance of the water quality objective. And so that's a whole nother 4-hour thing I could tell you about that I'll pass on now, but SWAT really has to do with the root zone. So basically, how did we do this? We had those calibrated crop models through the MPEP. Next thing we did was we took basically 4 years of grower data for the Central Valley and looked at the whole range of how these various crops are managed. What's the relationship between fertilizer and yield? How many sort of unique combinations are there? What's that look like? So our whole idea was to basically say, instead of, these values need to be calculated regularly, right? Whether it's 1 year or 3 years, it's not really decided yet, but regularly. And to go through and, reset up a SWAT model, it's going to be expensive, right? And laborious. And so what we opted to do was basically automate SWAT and run every possible scenario based on grower data up front and just do it all, right? And then every year from there on out, if you need to compute a value, you just do a lookup table, you access your database of all these SWAT runs, right? And so basically we pull our data together, we build the root zone library, which is that big database, which just leverages an automation framework. So for each crop in the valley, we have, hundreds and hundreds of runs that you can, for all the HRUs, right? And you'll see it visually in a second here. But they build that big database. And then eventually after that, to compute the values, it's just a function of taking that grower data. So your crop, applied N, your yield, where it is thanks to the parcel information. So you can relate it to a soil and a climate. And that's how you get your leaching estimate, right? So it's pretty cool process. So at the end of the day, again, we have about 129 crop models. Each of them we simulated anywhere from about 500 to more than 700 times to get the complete range of fertilizer rates and yields. And so kind of at the end of the day, we have this database that's got, more than 500 million, HRU specific data points for every crop in the valley, right? So you might not be growing, almonds on a given parcel today, but if in 5 years you are, and you manage it like someone else has in the past, we already have a model run for it, right? And so it's it's really going to pay it forward in terms of utility for the grower coalitions. Little nuance here, right? You can see that, for an example crop, if we look at fertilizer rates relative to yields that we're modeling, we don't have any runs that, have really high yields with really low end rates, right? It's not physically possible. SWAT is good like that. Won't even let us do that unless we were to really tweak our parameters way beyond what reality would suggest. And so, I don't really have it super detailed in this presentation, but there's a lot of QA, QC and review. You're making 500 million data points. You got to have some way to check them all. And we did a lot of checking because it matters. But yeah, just kind of a neat little agronomic thing there. And so, how does this all work? If we take an example township in the Central Valley, and here you can see all the various modeling, you can see all the various modeling units and the parcel boundaries outlined in black. If we were just take one example parcel, which actually has 6 different soil mapping units within it, for each of those mapping units, whatever the crop reported is, we have all of these various runs, right, for different fertilizer rates and yields. And so depending on what that grower says they applied in terms of fertilizer, what yield they got, we actually find an appropriate model run for each of those 6 soils in that parcel, right? So going down to the subfield scale, we do that for every parcel in the township and then roll that up to the township scale to get your actual value. So it's subfield all the way up to that. So quite robust. So kind of a neat framework there. And so the values themselves, and I think I'm kind of hurting on time here a little bit, but so we have there's a comprehensive report. If you guys are interested in it, just let me know. I'd be happy to share it with you. It's got a lot of details about our SWAT models, about our approach. Happy to share that with you. There is basically a list of requirements that we needed to satisfy as part of the regulation to use a model, right? There's always questions about transparency and accuracy, right? And so we have to demonstrate, we have to be transparent about what we did. We need to demonstrate that it's reasonable. And so basically there's more detailed reporting beyond just, here's the leaching number for this township that we provided in that report. And some of that might be quite interesting to you all. There's particular interest in, where are we modeling this nitrogen to go, right? Because if it's not going to leaching, it's going somewhere else, right? And so if we're basically off on any of these other nitrogen pathways, it's going to impact our leaching number, right? So we need to be transparent about that. So, one of the nice things about SWAT, you get these really detailed output files, right? You can add columns and get more output, which is what we ended up doing. So basically for each township, we have these super detailed summary tables of total nitrogen balances, total water balances, acre weighted average, so that the regulator can look and compare it against the grower data and see, what is it that we modeled, right? And, does this all make sense? So this is kind of a transparency component to help everyone just understand a little bit what we did. We also did sort of a comparison to some existing field study data. And so we did that actual process of, we know where these field sites are in the valley. We pulled out the HRUs from those field sites. We took the fertilizer rate that they said they were looking at. We took a leaching estimate. We compared that against what was measured. And I mean, this is pretty amazing to me. Granted, these field studies inform our modeling, but at the same time, to kind of independently go through this value calculation process and see that for almond and pistachio, we have a really strong correlation. And on the low end, we're actually overestimating. So we're conservative in terms of losses with the SWAT model. That was really quite neat. And then we've also done a comparison with Hydrus 2D, 3D, and actually Isaiah and his former postdoc IL helped us with that. And so basically we plugged in the same management, same soil, same climate, reflected a crop the same way in Hydrus and compared the results. And that work was actually published recently in the Journal of Hydrology. So we got comparisons to fields, we got comparisons to other models. We have a lot of transparency in terms of what it is we've simulated. And then moving forward, again, working with Isaiah and other researchers here at UC, we need to continue to validate our model, right? And so we're very grateful and fortunate to have collaborators and partners that are doing a lot of fate and transport work that we can then use to further confirm our leaching estimates. And so this is just some imagery of a Sensoil system that Isaiah, him and his team are installing in an annual cropping field up in, I think this is Yolo County. So really, really cool system. And just for the sake of time, I'll not go too far into it, but basically it gives us a really nice data series, time series of, fate and transport of water, nitrate through the root zone and down through the vadose zone, right? And so it's like suction lysimeters, on steroids times 10. And so Isaiah's installed now, I think, 3 of these systems throughout the valley. So we have one here in an annual cropping system, and then we have one in a nut crop system, and then one just installed in a citrus system. And so we can use this field data to, again, validate our model. So that's just some more information on that. Heavily monitored, right? So there's monitoring wells, there's eddy covariance station, so we can kind of dial in the water budget and the nitrogen budget in a real way there. So that's the kind of thing that we need. And again, this is why it's, sure, we're with the private sector, but we can't do all this, right? We need to collaborate and work with folks that really know how to do this stuff. So just one final thing, really nice, outcome from all the SWAT modeling for nitrate. Sure, this library can be used to estimate how much leaching is occurring, but it's also a really valuable resource for our coalitions to figure out, where to prioritize their efforts in terms of reducing load reduction, how much load reduction can they anticipate, how do they use all this output to kind of guide and prioritize and ultimately move towards those targets of like how much leaching is actually okay to be protective of water quality. So it's not just estimating today. There's, a lot that can be done with this data set, and it is being done with this data set moving forward. Okay, I'm sure you're almost falling asleep here, so I got just a couple more slides on salinity. So another regulatory program called CV Salts. This is actually a stakeholder-driven process, right? So stakeholders came together and said, we want to put a program in place to collectively and collaboratively manage salt over the long term, right? Over the 100-year kind of scale. So no one made them do this. And so under that process, there's what's called a prioritization and optimization study. And basically that study is just trying to figure out, how do we prioritize and optimize management strategies to protect water quality from salinization over the long term, right? And so kind of nested within that is a modeling framework to help answer some of these questions. And so we're actually linking up our CV SWAT model to a number of other models specific to the Central Valley. You can see CV SWAT is sort of right there in the middle, but we are connecting it to a Delta salinity model. We're basically taking water management information from DWR's tool about reservoir ops, water deliveries to irrigation districts, those really important things. Connecting it to groundwater models to inform, salinization over time, looking at crop impacts to salinity. And, we're exploring using the CV SWAT salt module to do that in the early stages yet, but hopeful about that. So basically linking up every kind of piece of the system into this framework so that, we can kind of conceptualize and think about strategies moving forward. And so this is, I think, my final slide. But so all the previous work on the nitrogen side was with ArcSWAT. And now we have transitioned to SWAT Plus to do this salinity work, right? So there's more features and more flexibility in the SWAT Plus framework to address some of the things we need addressed for this particular purpose, right? So what's really important with, kind of this phase of the modeling is we need to basically know where water is coming from, what areas are irrigating with what sources of water, whether that be from a, Sierra Nevada based reservoir, are they pumping groundwater, what's the salinity concentrations of those respective water sources, how much conjunctive use is there, are they supplementing surface water supply with groundwater, all of that matters, right? what are the other sources of salt discharge into the system, right? Whether that be a wastewater treatment facility or a food processor, winery, oil and gas, all these various salt sources. So we need to get all of that into this model, right? And so on the nitrate side, we're basically just running 1D root zone models for every field in the valley. But now we need to connect hydrology, we need to connect water management and these other salt sources. And so it's going to be, we're still working on it, but it's super comprehensive, super robust tool. SWAT Plus kind of has the features that we need. And we've been actually able to work with a number of the developers to kind of help us implement this. And so we're folding in a newly developed rice module. It's 500,000 acres of rice in the Sacramento Valley, so pretty important. Working with Ryan Bailey over at Colorado State to get the salinity module integrated. So it's really a collective effort, and the SWAT folks have been super helpful in helping us get this off the ground. But so we'll have Central Valley scale model, we'll have some local further refined models, and then we'll do, over time, develop various scenarios to test out in the future in terms of, salt management strategies or, various climate change scenarios. What happens as land use changes, say under Sigma, you have land fallowing, things like that. Many things is a dynamic place, and we're in dynamic times from a regulatory and environmental climate setting. And so, having various scenarios to look out, see what may come is really important. So that's a lot, but I think I'll just pause there and take any questions if there's time for that.
Thank you, Ken. Any questions in the room or online?
Okay, can you explain what's the root zone library?
Yeah, so the root zone libraries, when we automated SWAT, it's just basically all that output from that automation process. It's just a big database of all of our different runs and fertilizer rates and yields for each crop on each soil and each climate. Yeah.
And when you compare with the just 2D or 3D, because in SWAT it's like all one process, right? It's just vertical.
Yeah.
But now how do you compare to one?
Yeah, it was really interesting. I would say, remarkably, the hydrous is much more detailed in terms of, solving Richard's equation for flow.
Yeah.
Our hydrology was actually quite similar. So in terms of our estimates of percolation below the root zone, remarkably similar. And I guess when you have an irrigated system, most of the rain most of the water is pretty predictable when it happens. There's some alignment there. So that was a really neat finding. And then on the nitrogen side, I'd say they were comparable, but at the same time, there were differences. And it kind of boils down to how each model reflects, key components of the nitrogen cycle. And so in the case of SWAT, right, like you have an actual growing crop, a portion is, harvested, you have residues, those residues break down, right, and that nitrogen in the residue mineralizes, right? You have soil organic matter mineralizing. So all that is kind of like process based, where, in the version of hydrous that we use, we kind of had to empirically represent some of these processes. And so there's just kind of an inherent disconnect in terms of their representation. So that manifests a little bit on the nitrogen side.
Okay.
Yeah.
Thank you.
Yeah, sure.
Thank you. It's great presentation. So, maybe I can see something here. So could you please give us a little bit more information about the special extent of the model and how the calibration was done and the model simulation?
Sure. So basically we broke it up into 3 watersheds. So we have essentially 3 domains that we're modeling: the Sacramento Valley, San Joaquin Valley, and Tulare Lake Basin. So that's where our simulation and our calibration was done. And on the side of the crop models, again, that was sort of a manual iterative process to calibrate to ET, growth, nutrient uptake, yield, so on and so forth. And on the surface hydrology side, we weren't really focused on that. And so we didn't do a whole lot of calibration initially on, stream flow and things like that, so there's not really much of that to be said. Now, with the adaptation for the salinity project, that is obviously paramount to the question. And so that's something that we're working on at this point. But here's the 3 watersheds that we ran. And a lot of this, where's my cursor? I'm not sure if you're familiar with the Central Valley watershed, but this is including the Sierra Nevadas and the Coast Range, and really a lot of the detail and the action is down here on the Central Valley floor.
Essentially, more carbon requirements in low land,
Yes. Oh, yeah. Oh, yeah, for sure. And then some.
including Delta.
Yeah, we have the Delta, but DSM-2 is probably going to give a better picture of what's going on there in terms of hydrology. Yeah. Pretty complicated.
Next question from the people online.
It was really inspiring today. My question is more from the nutrient management perspective.
Yeah.
I heard, it seems like you have a really good solid data from the add-on. I
Mhm.
wonder, when you calculate infection minimization factor, I heard from the report that there is central carbon model, including the SWAT. These carbon affect a lot in the nutrient processes. Do we include that?
Mm-hmm.
Also for initialization for nitrate and soil carbon pools, do you have the data in soil?
Good questions. To answer one of the last one, in terms of initialization of nitrate, we didn't worry too much about that because we basically ran the model for about 38 years. And so whatever the initial setting was, that kind of comes out in the wash on the nitrate side. Percent carbon is incredibly important. Basically we went in and actually did some slight modifications to the code because, SWAT will have an algorithm to, assume a C to N ratio to define how much organic nitrogen is there at the initial state based on how much carbon you have. And so, rule of thumb, a lot of people use like 10 to 1, right? But we know in areas like the Delta, really high organic matter soils, histosols, you tend to have a much higher C to N ratio or a relatively higher C to N ratio. And so we actually scaled that initialization based on, percent carbon at the beginning. And I'm almost certain that, SWAT is considering your total carbon pool, and it's looking at C and N ratio to basically drive mineralization or influence mineralization, as well as temperature and moisture content. Yeah, sure. I did my master's on mineralization, so I was definitely in the weeds on that one.
My current degree of nitrogen.
Excellent.
Ken, we have some questions online. The first one, how may SWOT results be used to guide growers and management decisions?
Yeah.
Then when you answer that, I'll bring out the second.
Yeah, well, that's a really good question. Basically, once you have a good calibrated crop model, where nutrient demand and water uptake are sort of well-defined, you can really start asking questions about, fertilizer timing, how is that, the SWAT has nitrogen stress functions, right? So if you're under fertilizing, you actually get impacts on growth and yield, right? So you can kind of get down to the weeds in terms of, how you specifically time and at what rates you're applying fertilizers to your various crops. And then at sort of the scale with the root zone library, basically what we have is, a whole array of different management scenarios and leaching outcomes, right? And so basically you kind of have a prepackaged simulations where, some of the modeling assumptions are just the same through all of those, but you can still get a sense of, is it possible or is it probable that, I can get comparable yields under, lower fertilizer rates, for instance? Do I need this much fertilizer to achieve this yield? And so SWAT can help inform those sorts of things, as can the grower data itself, really.
And the second question was, wouldn't the use of pedon decrease leaching as compared to soil with regards to drainage loss and soil?
I don't think so, especially in the way that we modeled it, because essentially what we do is, again, we run it for, 38-year time period. And then in terms of what we actually use for a leaching estimate, it's the long-term average, right? And so basically, we essentially model it such that, our irrigation assumptions do not result in any net accumulation of nitrate in the profile over time. And so, all that residual nitrogen, you applied minus removed, you have that N balance, all of that goes somewhere, right? And so, to the degree that, your residence time is increased or you have like waterlogged conditions for longer, you have different soil organic matter characteristics, you could have some differences in gaseous loss and things like that. But we're not just taking a single year's run to estimate these things. And so I think some of that uncertainty is sort of handled in that way.
Can I extend the earlier question? Say if I'm a local farmer, so you have already run your different scenarios with different crops and everything. And can it be used for help the local farmer decision making? Say, I look at the future next year, weather is look like, I look at the scenario to provide by the root loan, and help me decide which crop should I plant or how much fertilizer can be used for on that regard.
Yeah, I mean, probably not the tool you need for deciding what crop you want to grow. But I should probably mention too that, there are sort of other tools out there that are really intended to help sort of make real-time informed decisions, like in-season decisions about management, right? So I'm not sure if you heard of Crop Manage, right? But that's another model that basically is giving you recommendations sort of on a daily basis of whether or not you need to irrigate or fertilize. And so that's really, really tailored to answer those sorts of questions. Whereas, SWAT can do some of those things, but in terms of like utility for a grower, I think there's probably other tools that would really help, make a decision within the growing season. Yeah.